All right, let's do an overview of stellar evolution. For this is for today, we're going to do small star stellar evolution, and what that means is small stars are less than about we're going to say 8 times the mass of the sun. About. There's a little bit of disagreement on that, but somewhere between 7 and 10. Stars of this mass are going to roughly follow the following timeline. Okay, a couple of principles. That'll make everything easy. And you probably know these already. One principle is if you heat a gas, it expands. And actually, let me say this a different way, because some of this occurs in a slightly different. Let me say it a little bit different way. If you heat a gas, it will expand. That's true. Let's talk about the action on a gas. So if I compress a gas, it heats, right? If you pump up a bicycle tire, the pump and the bicycle tire are going to get warm because you're compressing a whole bunch of gas into a tiny, smaller area. If you compress a gas, it heats. If you expand a gas, it cools. This is easy to see. If you ever have a can of compressed air or something like that, spray a little bit of it, get your hand far enough away so you don't hurt yourself. But if you spray a little bit of air on your hand, it cools. It's going to feel very cool to the touch. In fact, you can make ice with it. Okay, so that's one principle. Here's another one. If this is the sun, let me make a nice circle. If this is the sun, the principle is that the outer layers of the sun all want to fall in towards the center, right? Because the sun is just a ball of gas. There's no solid surface or anything. So this is the force of gravity. Gravity is always trying to make the star smaller. It's always trying to compress the star. But why doesn't it compress any more than it does? Why does the sun have the size that it does? It's because something is keeping the sun inflated. If you want to think about it that, if it's like a balloon, there's some force that's keeping the sun inflated, and this is the force of radiation, right? Almost like it's trying to blow the sun up. So the sun is always in balance between these two things. There's the radiation pushing out, the energy trying to get out, and then there's gravity trying to pull the sun in. This balance is called, in the book, hydrostatic equilibrium. Right? I suppose that makes sense. Hydro actually means having to do with gases or liquids, but static equilibrium just means that something doesn't change. So that's the balance between gravitation and radiation. That gives the sun its size. Okay, the sun actually regulates itself. Your body does this. People do this. What happens if you get too warm? You sweat, right? It's an unconscious thing. And by sweating, you will lower your body temperature because of evaporation. What happens if you get too cold? You shiver. And that's the body's response to being cold, because what shivering does is it warms up the muscles. And so as soon as your body starts shivering, your body warms up. That's why you always get like chills before a fever. Okay, so your body does the same kind of thing. It fixes itself so that it roughly stays, no matter what happens on the outside, it stays within a narrow band of temperatures that we need to have in order to live. Stars are kind of like that. They have their own kind of a thermostat. So what would happen in the center of a star? And by the way, all the energy that stars produce comes from a pretty small area in the center. All the stuff on the outside is just an envelope. It's just gas. It's not really doing anything. So the energy is all coming from deep inside in the core. So what happens if there's more energy? If the core, for whatever reason that we'll talk about, what happens when the core generates more energy? Well, what happens is that there's more radiation pressure, right? The mass of the star hasn't changed. But if you were able to dial up, if you kind of had a knob and you could twist and make more energy come out of the core, well, the mass of the star hasn't changed, the gravitational force hasn't changed, but the radiation going out has. So the radiation wins a little bit, and what happens is that the star gets larger. It expands. So if the luminosity goes up, the star expands. And what happens when it expands? That outer envelope gets bigger. There's more area that the energy can disperse out of. The outer layers cool, right? And when they cool, they get more red. So when the star expands, the outer layers cool. Okay, neat. What happens if, for whatever reason, what happens if the luminosity goes down? What happens if in the core you're not making energy as much as you used to? Well, what happens then is that the radiation pressure goes down and gravity wins. And so the star starts to contract. Well, what happens when the star starts to contract? When you contract, you're compressing a gas, and so it heats back up again. And so the reactions come back up in the core. So the star is sort of like a thermostat. If the reactions, for whatever reason, start going down, then the star contracts until they start going back up again. If there's too much radiation coming out of the core, then it expands until it cools back off, right? So stars tend to stay in this narrow band that's a balance between the radiation and gravitational pressure. Oh, let me finish this. If L goes down, the star contracts. And heats. Okay, so those are the principles. Now, for the sun, what happens in the sun? All right, so in the center of the sun, remember how it works. 4 hydrogens are being converted to helium, right? A whole bunch, 10 to the 30th times or whatever, 10 to the 37th times per second. So this is constantly going on in the center of the sun. What happens to the helium? Well, helium has 4 particles in the center, and helium is more dense than hydrogen. It's a bigger particle. So what it does is it sinks, just like throwing a rock into a pond. It sinks down to the bottom, and so what you get is, what starts to happen is that the center of the star, I can draw nice circles, the center of the star starts to accumulate helium. And around it is a layer, a shell, where hydrogen is being converted to helium, right? But this inner helium core is inert. All I mean by that is it doesn't shine. There's no energy being generated in there. The reason why is that it needs to be about 100 million degrees for helium to fuse, and I'll talk about how that happens in a minute. Remember that in order for hydrogen to fuse, you need to have a certain temperature because the protons are repelling each other, and so they have to be traveling really fast to get close enough to fuse until those hooks kind of take over. It's worse for helium, right? Because helium is heavier, so it needs to be a lot hotter for it to travel faster. And then each helium has 2 protons, so there's 4 times the charge, and it's actually even worse than that, which we'll say in a minute. But it has to be a lot hotter in order to get 2 helium nuclei close enough to. So the center of the sun is not that hot. It's right now only about 16 million degrees. You need about 100 million. So the center of the sun is just building up this core of inert helium, and it's not doing anything. In fact, what's happening is that the entire weight of the star is crushing that core. It's crushing the helium core. So constantly, the helium core is being crushed and heated a little bit more over time, all the time. So what happens when that helium core is being crushed and heated is that it drives, it's sort of like blowing kind of bellows on a fire. It's heating up this layer a little bit more as time goes on. And those reactions, the hydrogen to helium reactions, are going faster and faster because they're being heated from underneath by that helium core. So the sun, what happens? The sun's core, oops. The sun's core is getting brighter. Its luminosity is going up. That hydrogen to helium layer around the core is going faster and faster over time. And it's generating more and more and more energy slowly, right? This is not the thing, and this can get confusing. This is not the thing that's responsible for global warming. That is a blanket on the Earth, right? Over the course of 100 years, 200 years, the output of the sun really doesn't change very much. What I'm saying is that over hundreds of millions of years, the sun's luminosity is going up because that helium core is getting smaller and smaller and hotter, and it's driving the reactions faster and faster. And so over a very long period of time, the sun is getting brighter. Now this we can actually see in the fossil record. It's kind of cool to look up. We can go back and see that in the distant past, we can look at fossils of ancient plants and so on. And we can see that the sun used to be dimmer in the past, 20% dimmer, 30%. So the sun does keep on getting brighter and larger, right? Because remember, if the luminosity goes up, the star expands. So the sun is getting a little bit bigger over time and a little bit brighter over time. And again, not over the course of a human lifetime so much as millions of years, hundreds of millions of years, it gets noticeably brighter. So this is a slow, very, very slow effect. Okay. But it does happen, and it accelerates. So at some point in the future, what happens is that these layers eventually, these outer layers have expanded so much at the end of the star's life that the sun becomes a red giant. At this point, there's a little bit of disagreement about whether the sun will go all the way out and encompass the Earth. We don't know if the Earth will be inside the sun, or it's possible that the sun will expand to just almost where the Earth is, almost out to the Earth's orbit. There's a little bit of a discrepancy, 5 or 10% discrepancy. I might suggest that in terms of the well-being of the Earth, it doesn't make much difference if you're inside the star, the outer layers, or just outside the outer layers. Either way, the rock vaporizes. The Earth is going to be blown away. Puff of smoke. Eventually. This is 5 billion years from now. So eventually, the sun will swell up to become a red giant. After that point, what you get in the core, and then the core is greater than 100 million degrees. All the time, that inert helium core has been getting hotter and hotter, right? Well, at some point, it's going to cross this threshold of 100 million degrees, and this will happen after it's already a red giant. What happens then? What happens when helium fuses? Okay, it's kind of a cool story. What happens when helium fuses? Well, let's see. Helium looks like this. 2 protons, 2 neutrons, and then here's another one. Oops. Let me try that again. Neat. Okay, so I've got helium, and remember this is helium-4 and helium-4. Remember this is 2 protons, 2 neutrons each. All right, so if they combine with each other, if they fuse, what do you think you get? Well, your first inclination is that you get something with 4 protons and 4 neutrons, right? What element has 4 protons? What's element number 4? Beryllium. So this is what you think you would get. That's perfectly reasonable. It turns out that's not what you get. Nature is a funny thing. The helium nucleus, that combination of 2 protons, 2 neutrons, is so stable that nature loves it almost above everything else. So what happens is that beryllium will form, but only for about 10 to the minus 18 seconds. A millionth of a trillionth of a second. It's something like that. I'm within a factor of 10. So this forms, but only really, really briefly. And then what happens is it falls back apart again. It's much happier being 2 helium-4 nuclei. So they don't fuse. You really don't get any energy out of it. It doesn't happen. So what really happens is that the 2 heliums come together, they stick for a very brief period of time, and they just sort of bounce off and they go on their separate ways. So it's almost like a collision, right? So beryllium, it turns out, can't be made this way. But here's what people realized. This was, 1940, something like that. The puzzle was, how do you get past this step? Because it was known back then that beryllium, this form of beryllium, is not stable. It falls back apart. So what has to happen? And the clever realization was, it's so dense. Remember, the inert helium core has been compressed for hundreds of millions of years, for billions of years. It's been compressed and heated. It's so dense and so hot that the following thing could happen. What you could get is a helium-4 and a helium-4. They could come together, and then it's so dense and hot that this could happen. You get another one. You get a third one. In other words, it could happen that you get 3 things colliding at once. And understand how rare. Normally, that would be an incredibly rare thing, right? It's hard enough to get 2 things to bounce off of each other and interact. But now you got to get a third that comes in and hits at the same time within that 10 to the minus 18 seconds. You got to get a third one to come in and hit. But what happens when you do is that you combine these 3 things together. And then what do you get? Well, you get something with 6 protons and 6 neutrons, and it turns out that that is very stable, and that is carbon. So, for historical reasons, this is called the triple alpha reaction. It used to be, in the old days, they used to call helium nuclei, they called them alpha particles, because they didn't know what they were, they just named them. Later, we learned that they were helium nuclei. But anyway, if you have 3 of them, the triple alpha, you can get carbon. This is how helium fuses. This is why it needs to be so dense and so hot that it skips over beryllium. And we'll come back to that next week. That's sort of an important thing. Notice, we skip right from element number 2 to element number 6. We skipped right over elements 3, 4, and 5. So that has consequences. You could imagine, if this is the way that stars operate, you could imagine that elements 3, 4, and 5 might be pretty rare in the universe because stars have a hard time making them. And we'll see next week, but that turns out to be exactly right. When you look in the universe, elements 3, 4, and 5 are incredibly rare. So nature skips right over them, and stars generate from helium to carbon. Stars can build carbon from helium. This is where all the carbon in your body came from, was from these stars, ancient generations of stars that built carbon this way. The sun doesn't do much of this yet, right? Because the core isn't 100 million degrees yet, but late in the sun's lifetime, this is what's going to happen. And then what happens is you build up. I mean, it's the same thing, just sort of running faster. Now, after the stars already a red giant, you build up a carbon core, just like we did helium before. So carbon starts raining down, sinking down to the center, and then around it, you might have a layer where it's hot enough for helium to burn to carbon, and then around that, you got a layer where hydrogen burns to helium. So you start to get this sort of an onion skin layers of fusion that are going on. And then at the very center is carbon. But carbon can't fuse unless it's 600 million about. So now you have to wait to get 600 million degrees in order for carbon to fuse, and the short story is it's never going to happen. For the sun cannot generate those temperatures in the center. Why? Because the sun's not massive enough. Where does the energy come from to generate the heat in the center? It comes from the gravitational pressure of the star pushing down on itself. And the sun just isn't that massive. The sun's never going to get, the core of the sun is never going to get to 600 million degrees. And so at the end of the sun's lifetime, after it's already a red giant, what happens is that the carbon core gets hotter and hotter. It drives these reactions faster and faster. And again, the sun starts to inflate and swell even larger. But this time, it swells so rapidly that nothing stops it. And what you get is the outer layers of the star just float away. And they float away and become what's called a planetary nebula. Understand when they say planetary nebula, it's got nothing to do with planets. It's only because when they looked at them, you should look up pictures, they're gorgeous. When they saw pictures of these in the early days, the idea was that they didn't know what they were. It's just that they had sort of a disc-like appearance and they looked a little bit like planets, but they also look fuzzy like nebula. So they didn't know what to make of them. So guess what? They just combined the names and called it a planetary nebula. But now we know that they are the late stages. We're witnessing the deaths of small stars. The outer layers are floating away because of the rapid expansion. And all that's left at the end is that carbon core in the center, the hot carbon core that's not burning, right? It's like a giant ember. It's just sitting there. And that carbon core is what we call a white dwarf. And we'll talk a lot more about these next week. But a white dwarf is what's left over. It's sort of the corpse of a dead star. It's not even right, really, to call white dwarfs stars. They're not stars in the same way that the sun is a star, because white dwarfs aren't burning anything. They're just hot. It's just a hot ember. And they slowly cool down over billions of years. They become white dwarfs, then yellow dwarfs, then orange dwarfs, and red dwarfs, and so on. But they're not burning, right? They're just sort of burnt out husks of stars. But this is what we see. Sirius, I think the closest one to us that I know of is Sirius, the brightest star in the sky. It's a type A star, and it's got a little companion. It used to have a binary companion that now is a white dwarf. It used to have a binary companion that was much larger, but it's already evolved and it's already died. And so all that's left is sort of the corpse of its companion is circling it. I guess that doesn't sound like it's the way it is, right? That's nature. So this is the life cycle of a star that's like the sun. Hydrogen burns to helium. The helium inert core gets hotter and hotter. Eventually it drives an expansion. The sun becomes a red giant. And then helium, as soon as you cross 100 million degrees. Oh, by the way, in the sun, whenever you cross this threshold, the helium has been packed away, packed down for these billions of years. And then you suddenly cross this threshold where helium can fuse. And so what happens is that it's not a slow process. About half the core just goes. It's like lighting a keg of dynamite. And so this is called helium flash. The danger in calling it that is you might imagine that this is what causes the star to become a red giant. But remember, the star is already a red giant when this happens. And the size of that helium core is really, really tiny compared to the star. So when the core goes, when there's helium flash and all this is converted over to carbon, it doesn't really affect the luminosity. It doesn't, in fact, it has a negative effect on the luminosity of the star, because what was really driving the luminosity of the star is that hydrogen helium layer on top, and this sort of blows it out from underneath. And so what happens in detail, I think the book goes into this a little bit, is that the star actually shrinks a little bit. You might think, oh, helium flash, that's like the star exploding. That's not what happens. It's just the tiny little core that just goes pop, and it blows out the layer that's actually creating the energy, and the star actually gets a little dimmer until it starts heating back up again and then starts expanding, that second expansion. So anyway, this is an overview of what's going to happen to the sun. You already might get a sense of what's different about this as compared to massive stars. Why do we say there's a distinction between stars that are, 8 solar masses and less, that go through this process, and then stars that are greater than that? What can massive stars do that small stars can't? They can do this. So the sun will never be able to fuse that carbon. It's just left over, and we see it as a white dwarf. Massive stars can drive the temperature up over 600 million degrees, and massive stars can fuse carbon. And then a whole other series of events start sort of cascading downhill, and it becomes very exciting. That's next.